Okay, let's work on problem 1289 from chapter 12 of your textbook. Problem reads, what mass of sodium chloride should you add to a liter of water in an ice cream maker to make a solution that freezes at minus 10 degrees Celsius? Assume complete dissociation of the sodium chloride and a density of 1 gram per milliliter for the water. So this is an interesting problem. A lot of people like to make homemade ice cream. To do that, you basically combine the ingredients and then you have to freeze it, okay? And very typically, you need to make a very, very cold solution that surrounds the ice cream to freeze it. I'm sure you can find some YouTube videos that describe that process in detail if you're interested, okay? But here, what I'm diagnosing just from this paragraph of information is that we got a freezing point depression problem. And that's definitely the case, okay? I chose this problem because it's an example of an ionic compound that dissociates in water, and it's going to basically need us to consider this Van Hoff factor, and that's why I'm really working. Okay, I wanted to show you an example, one like that, because some of the other videos didn't include that. Okay, but we know we've got a freezing point depression problem because we're depressing the freezing point of an aqueous solution by 10 degrees. Okay, so basically what that means is that we know our delta TF, our change in freezing point, is 10. It's 10 degrees Celsius. And in accordance with the equations that we've learned about, I multiply 3 variables on the right-hand side of the equation: molality of solid, freezing point depression constant, and I, our Van Hoff factor. Multiply those 3 together, I got to get 10. All right? So what do we know and what are we going to find? What's our unknown variable? Okay. Well, I, remember, is our Van Hoff factor. It has to do with the nature of the solid. If we have an ionic compound, remember I, the theoretical value, is the number of ions produced per dissociation of the molecular or the formula unit of the ionic compound. Okay? So what I mean by that is we take one formula unit of the solid sodium chloride, throw it in water, those ions become hydrated or surrounded by water molecules. This is what defines the aqueous solution. Now when that happens, the ions break apart. So from one formula unit of NaCl, I can actually produce 2 ions in solution, 1 sodium plus 1 and 1 copy of Cl. So that's 2 particles for every 1 formula unit of this. And that's important for us here, because remember, these colligative properties depend upon the relative concentration of solute particles that are dissolved in our mixture. So this business down here in the problem where it says assume complete dissociation of NaCl, what that basically is telling us in chemistry lingo is that we can assume the theoretical value for the Van Hoff factor is what we would predict on the basis of the formula. In this case, that's 2. All right? So assuming the complete dissociation tells us that whatever the formula says the Van Hoff factor should be, we can assume that that's true. Now remember, in reality, sometimes that number can deviate for experimental values, but this problem is basically telling us that we should not consider that. All right? So moving on, we need a value for Kf. This is our freezing point depression constant. Remember, that's solvent specific. For water, it has a value of 1.86 degrees Celsius per molal. Okay? So we're making a lot of progress here. We know that when we multiply these 3 terms together, we got to get 10. But if we read closely in the problem, do we have any mechanism right now for finding the molality of the salt? We really don't. In fact, that's going to be our unknown. We want to know what mass must we add to the water to make this happen. Okay, so we don't know what that is. It's going to be our unknown variable. So I'm going to write my lowercase m there for molality, and we're going to work the problem. All right, now, clearly, we've only got one unknown in that problem, so we can rearrange algebraically. We can multiply this by this and rearrange algebraically, solve for m. And if we do that, we can quickly find that the molality is 2.688 molal. Again, that's the number that I just get off my calculator. I'm not paying too much attention here to sig figs at this point. But that's the molality of the sodium chloride that is required to make this happen, to get this 10-degree drop in the freezing point. And we're still not done because we want to know the mass, not the molality. So we have to remember our definition of molality. We know it's equal to 2.688 in this case. But we should really remember what that means. And of course, molality is the number of moles of solute divided by kg or kilograms of solvent. The mass of solvent expressed in kilogram units. Now, do I know either of those? Let's go back to the problem and read it carefully. I certainly do not know the number of moles of solid. If I knew that, I could easily find the mass of sodium chloride. But I do know that I've got a liter of water, and I'm going to add my sodium chloride to 1 liter of specifically water, not solution. I'm not going to make a liter solution. I got 1 liter of water. And that's important because that's my solvent here, and this specifies solvent. I'm also told that the density is 1 gram per milliliter. So if I do a little bit of sort of fumbling around here, and maybe this is obvious already, I can take this 1 liter of water, which is equivalent to 1,000 milliliters, right? And I can take that 1,000 milliliters and use my density as a conversion factor to figure out that I've got 1,000 grams of water specified. And 1,000 grams is equal to exactly 1 kilogram. Maybe that was obvious, maybe not, because the units are different, okay? But the beauty of that is my kilograms of solvent, my kilograms of water here is 1. It makes my life at least a little bit easier. So whenever you have 1 in the mathematics, right, things kind of simplify out, I think. And what we can see as a result of this is the number of moles of solute, here that's solid sodium chloride, that is required to make this freezing point depression happen, this 10 degrees, is 2.688 moles. If I add that many moles of sodium chloride to this 1 liter of water, I can get the freezing point to drop 10 degrees in theory, okay? Assuming the Van Hoff factor is in fact 2. Well, once we get to this point, we are in business. We again want to know the number of grams of sodium chloride that's required. We now know how many moles that's required. Surely we can do a moles to mass conversion by using the appropriate conversion factor. That 1 mole of sodium chloride has a mass of the formula weight of sodium chloride, which corresponds to 58.44. After doing the math, my calculator returns 157.0867 grams of sodium chloride. That's the mass that I need. To consider sig figs, go back to the original question. Looks like 3 is going to be our limiting factor here. So we should probably truncate this to 3 sig figs. And that's easily done just by rounding to 157. And that is my final answer. 157 grams into a liter of water will allow me to make my ice cream.